all at the University of Washington. Steve received his bachelor's in mathematics and a minor in control and dynamical systems from Caltech in 2006, and his PhD in mechanical and aerospace engineering from Princeton in 2012. He has done really groundbreaking work at the intersection of dynamical systems and machine learning, and his research combines the two to model and control systems in various domains, such as fluid dynamics, biolocomotion, optics, energy systems, and manufacturing. Steve is a co-author of 3 textbooks, and his work has garnered numerous awards, including the Army and Air Force Young Investigator Program Awards, the PK's Presidential Early Career Award for Scientists and Engineers, and the UW College of Engineering Junior Faculty and Teaching Awards. As you can tell, in addition to his seminal research contributions, I think Steve is also a very passionate teacher and has a very popular YouTube channel. I encourage you all to check it out if you haven't already. So if you have any questions during the talk, feel free to post them on the chat box. We will be monitoring the chat, or you can also unmute yourself to ask your questions directly. We're very excited, and without further ado, let's welcome Professor Steve Brunton.
Awesome. First off, thank you all so much for the very kind invitation to this seminar series, and also for the kind introduction. So it really is a pleasure to be here. And it's kind of cool. Like, of course, I would love to visit in person, but it's nice that virtually I can interact with so many of you, from different places. I will, just a shout out for those of you at Caltech, my wife and I will be on sabbatical there starting next year, actually starting in a couple of months this summer. And so, we'd love to interact more with lots of you there. Okay, and yeah, definitely reiterate, if you have any questions, please interrupt. I usually have about 3 times too much material in my slides. So, anything you want to talk about is what I want to talk about. And so we can kind of tailor depending on what you're interested in. I'm currently planning on talking a lot more about learning dynamical systems models, but we could also talk about data-driven control more directly. Okay, good. And I think you guys know that the recording stopped. At least I heard that. So I don't know if you guys heard that as well.
Yes. So like previously, the live stream is not working, but now the live stream is working. It's going to be, yeah.
Okay, perfect. Thank you. Okay, so before I get started, I want to acknowledge some really fantastic colleagues and collaborators and co-authors, partners in crime in this work. And this is really kind of a small snapshot of the larger group that I work with on these problems. Most of the data-driven dynamics and control work I've done with Nathan Kutz, who is my colleague here at University of Washington, and our fantastic PhD students and postdocs who I've listed below here. Actually, Krithika Manohar was recently a postdoc at Caltech with Andrew Stewart and is now a faculty member at UW. And a big part of my research focus beyond kind of machine learning for dynamics and control is in applying this to complex systems, particularly in fluid dynamics and in fluid turbulence control. And so most of that work is with Jean-Christophe Loiseau from Paris Tech and Bernd Nowak and Sam Tyra. So I like to show this movie of an eagle when I'm starting out, because I think it's really kind of inspirational for what kinds of characteristics we would like in kind of modern adaptive learning for control. And so I just want to point out a few characteristics of this eagle, right? So this eagle is interacting with an extremely complex, unsteady, turbulent gust field. You can almost feel the turbulence by looking at its wings and how it reacts. And it is interacting with this field with extreme kind of precision and robust performance. Even if it's raining or if it just had a large meal, it can handle this uncertainty quite well. It doesn't have, to our knowledge, access to the Navier-Stokes equations or a PhD in fluid mechanics or control theory. It doesn't have access to full 3-dimensional wake measurements behind its wings. What it does have is an incredible kind of experiential knowledge of how to interact with flow fields. It has sensors all across its wings and a great kind of inertial guidance system. And, you know, we can start asking questions. Why is the eagle able to achieve such incredible performance, right? If we as humans decided to build an engineered system, you know, just simulating it alone in this environment would be a supercomputer computation. And I would argue it actually is beyond our current capabilities if you really take into account not only the unsteady turbulent environment, but also the compliant wing surfaces and the feathers, the musculature and the kind of neuronal control system. The multi-scale aspect of this eagle in flight is truly staggering. So why is the eagle able to do this, you know, pretty fast and adaptively and online? So I would argue that the fundamental kind of advantage here is that there are patterns in this fluid flow field that matter for this eagle, for its daily life. Out of all of the millions or billions of small eddies that we would have to simulate as humans in the Navier-Stokes equations, there are large coherent structures and patterns in the flow that matter for this eagle turning and maintaining lift and drag and balancing its forces, in this case, to gently land on this rock. And the existence of those few dominant patterns is what facilitates sparse measurements. It doesn't care about all of the millions of eddies in the flow. It cares about these coherent structures. And so it only has to estimate those using its wing sensors. That also facilitates efficient kind of reduced order modeling, or kind of an embodied knowledge of what those structures are going to do, and robust performant control. And so that's kind of, I want that to be in the back of our mind. These are the things we want to be able to do for our systems. We want to be able to deal with limited measurements, uncertain knowledge of the physics. Of course, we're going to have very high dimensional uncertain systems we're interacting with, but we believe that they exhibit patterns. Okay. And so this is going to be my organizing diagram. My wife jokes that I'm a bit of a control freak. And so I try to put everything in the world into one of these two boxes. So everything I care about goes in this blue box, whether that's a fluid flow or an eagle flying. Maybe it's a network of neurons in your brain, or a model of a disease propagating across a continent. Everything I care about is in this dynamics block. And we're going to try to model that. And then with sensors and actuators, we're going to affect it through some control or some intervention to modify its behavior, to bring it into some engineering nominal behavior. And so a big portion of my lab really applies kind of modern methods in machine learning to build dynamical systems models for systems where we have only partial knowledge of the physics, where we might not even have a model like in the Navier-Stokes equations, or where we need a faster model to work with. And we put a real premium on models that are interpretable and generalizable. So I'll talk about that later. We often also bypass modeling that system entirely and go directly to data-driven control strategies, things like deep model predictive control, or reinforcement learning, or genetic algorithms, some combination of trial and error and educated kind of exploration and exploitation to learn control laws effectively. And again, we've applied this to lots of systems, including renewable energy systems and experiments. And then kind of the third major leg of what my lab works on, at least in a theoretical sense, not in the applied sense, is in using these advanced data-driven optimizations to identify optimal sensor placement and actuator placement. So again, when I think about a high dimensional system like a wing in a turbulent flow, let's say now we're talking about a Boeing wing or an airfoil, an Airbus wing, there are many, many locations I could put sensors on that wing, but I can't put sensors everywhere. So I might have to pick and choose the best locations. And this is somewhere where we take a lot of inspiration from biology. So this is actually a project I collaborate on with my partner Bing, is understanding how insects fly. So I showed a movie of an eagle in the beginning, but to some extent, I actually think that insects are even more interesting and impressive, because this moth, it's about the size of my hand, and it also interacts with extremely unsteady turbulent gust fields. For example, when its proboscis is in a flower, it maintains very good station keeping despite gusts and unsteadiness. And it has a much kind of lower end computational hardware, so to speak. Its brain is much smaller than an eagle's. It has a lot more primitive nervous system. And something I learned that I think is super interesting is that every flying insect, every single one of them, has on the order of tens to hundreds of strain-sensitive neurons distributed on their wings. And they use these, so they're literally neurons that when the wing bends, they fire. So they're sensitive to strain and they fire. They give sensory information to deformations on the wing. And they allow the moth to react to gusts faster than that signal can go up to their brain and back down to their muscles. They've done these laboratory tests and they react faster than their brain can process information and send it back to their muscles. And what that means is that these insects are actually taking this sensory information, they're assimilating it directly into local computations in their shoulder muscle, and they're feeding that directly back to adjust their wing beat frequency and pattern to react to these disturbances, which is truly remarkable. And again, that's kind of, you know, what we would like to be able to do as engineers. It's robust, it's distributed, it's very efficient local computations, and it gives you much higher performance and robust control because it decreases the latency. It doesn't have to be centrally processed and communicated and fed back. So they get much lower latency control in having this distributed sensor network. And so, you know, that's really important, as we all know, for control, to get that latency down. Okay, so these are kind of the big areas of work in my lab. So we use kind of machine learning for modeling, for control, and for sensors and actuators. Now, I love giving talks to technical audiences like this, but oftentimes I find myself giving this talk to, you know, senior business leaders, for example, you know, at tech companies or aerospace companies. And sometimes you get this feeling that maybe we are viewing machine learning kind of like a magic wand. Okay, you have some big hairy engineering problem. It's costing us, you know, $100 million a year, and you're going to point your magic wand, and poof, it's gonna go away. Apologies, I'm mixing my metaphors with Harry Potter and Gandalf here, but I wanted to dispel that and get us kind of on a common ground right now. So the way I see this, my way of pigeonholing the world, is that machine learning, it's basically what we've been doing for the last 70 years in system identification. It's building models from data with techniques in optimization and regression. And we've been doing this since at least Ho and Koopman and earlier, right? We've been building models from data for decades. But, you know, these are more powerful optimization algorithms on much higher end computational infrastructure with much larger and richer training data sets. And so it is a new paradigm of building models from data with optimization. But I just wanted to kind of dispel the myth. This is stuff we've been doing forever. And in particular, I want to point out that, you know, in any dynamical system that you find interesting, I'm personally interested in fluid dynamics. You might be interested in neuroscience or climate science, ecology or epidemiology, mechanical systems, you name it. These dynamical systems, the engineering tasks that we have, like dimensionality reduction, finding those patterns that matter for that eagle flying out of all the millions of fluid vortices, what are the ones that matter? Or reduced order modeling, taking something like the Navier-Stokes equations and getting the best three-state ordinary differential equation that characterizes the behavior, or optimal sparse sensing or optimal control. All of these tasks that we care about in blue as engineers tend to boil down to hard optimization problems. Okay, and they're hard because typically the governing equations are nonlinear and our numerical representations are high dimensional, like in Navier-Stokes or a disease model. And what this results in is highly multi-scale non-convex optimization problems. Lots of local minima, very hard to find a global optimal solution. And so again, our engineering tasks at the end of the day boil down to really hairy optimization problems. And so if there's one takeaway, I want you to take away that machine learning are essentially a growing suite of techniques that give you really, really enhanced optimization capabilities if you have a rich enough data set. Okay, so that's kind of why these fit so naturally together. We can use machine learning for control because they're both optimization problems. One solves an optimization problem, the other is an optimization problem. Okay, good. And what I'm going to talk about, I'm going to spend most of my time in this kind of modeling dynamical systems from data world, kind of learning the dynamics. And I want you to, in the back of your mind, be thinking, you know, of course we could do model-based control once we have these models. We could use these for model predictive control, which is a great, I personally love model predictive control. I think that's one of the best approaches to robust adaptive control. And so we're going to try to learn efficient and accurate dynamical systems models so that we can use them for model-based control. If you're interested, towards the end of the talk, I can talk a little bit about some of the model-free control approaches as well. But again, just interrupt if you have any questions or if you want to know kind of how things connect. So x dot equals f of x, that's our starting point for most or all of model-based control and dynamical systems. And in some sense, the nonlinearity of f is what keeps us all in business. If this was a linear dynamical system, things would be pretty easy. We could go home early. We would just use, a one-line MATLAB or Python command to get the optimal controller or optimal estimator, and we'd be done. Or get a reduced order model that's optimal. All of these optimization problems are easy if our dynamics are linear. But nonlinearity is kind of what keeps us in business. Now, the first challenge, so I'm going to talk about some challenges I see in data-driven dynamical systems and learning dynamics from data. The first big challenge, and this one sometimes it's such a big challenge, it's like a blind spot. We almost don't even recognize that this is a challenge sometimes, is that in many systems of interest, we don't even have governing equations. We don't have F equals ma for the brain or for an epidemiological system. We can't agree on the equations for the climate or for neuroscience. Even when we have equations like the Navier-Stokes equations for a fluid, it's far too cumbersome and unwieldy for real-time design, optimization, and control. And so we need to discover unknown physics and unknown equations for systems like neuroscience and climate science and epidemiology. And we also need to discover effective reduced order models, even where we have the governing equations for things like seismic activity and elastic equations and fluids equations, continuum PDEs in general. Okay, so that's the first challenge that we work on in my lab for data-driven modeling, is discovering equations. The second one, again, is this issue of nonlinearity, that nonlinear dynamics are poorly understood. And for each of these challenges, there are going to be tailored machine learning approaches that allow us to start tackling these. Okay, so nonlinear dynamics are really challenging. And essentially what we're going to do is try to learn coordinate transformations, a new coordinate system where the dynamics become simplified or even linear. Okay, and I'll point out, just so the back of your mind, for the last 2,000 years of history of mathematical physics, the great breakthroughs in equation discovery and physics discovery have come after a great breakthrough in coordinate systems, a new coordinate system that unlocked some mystery of how the dynamics work. So think about Isaac Newton and Kepler. Their breakthroughs came after Copernicus put the sun back at the center of the universe, or sorry, our solar system, not the center of the universe. Similarly, right, the Fourier transform is a coordinate transform that linearizes the heat equation, that simplifies the heat equation and allows the dynamics to be more simply represented. Okay. And then the third challenge, and this is one that we all deal with on a daily basis, is kind of the big data challenge. We have more measurements than ever for high dimensional systems. We can get millions or billions of measurements as a time series for fluid systems, for disease systems, for cell phone networks and power grids. And so how do we find the patterns that are going to facilitate the tasks above and efficient sensing and control? And I actually think I'm going to start with the bottom one, because this is kind of the most obvious low-hanging fruit for machine learning techniques. So patterns exist in your data. That is the fundamental property that allows us to do modern high-performance computing and modeling for fluid flows and elastic systems and kind of continuum mechanics in general. This idea that there are patterns that emerge that are pretty simple. So in this cloud flow over Rishiri Island in Japan, we see that even though it's an extremely complex high-dimensional geophysical flow, we have this emerging Kármán vortex street that is reminiscent of much, much simpler low Reynolds number flows that we know can be described by 2 or 3 ordinary differential equations. I actually found this great video illustrating this effect on Twitter. So this is a video stream of the flow over Guadalupe Island. And again, you can see this kind of clear emerging pattern in the data. And so at least in fluid dynamics, we have been using these patterns for 5 decades, right? Since the 1970s, we've been using these coherent structures to get a coordinate transformation, again, a new coordinate system where our data or our dynamics looks simpler. And so we call it the proper orthogonal decomposition, or POD. It is the same as principal components analysis, and really it's a singular value decomposition. You take your data, you SVD it, and you get a reduced rank representation that in some sense, an L2 sense or for Frobenius sense, is kind of optimally capturing that data. And if you want, you can think of this as a generalized Fourier transform. So you could just FFT your data in space and you would get, spatial modes. But this is kind of like a tailored Fourier transform that's tailored to your specific data, to your specific geometry, and to your specific physics. Now, this is old technology. This is, if you really want to call it old machine learning, you could. You're building models from data using optimization and regression. And you technically could write this as a neural network training problem. You could solve the POD, PCA, SVD problem using a shallow linear autoencoder. So your high dimensional data would go in as X, and the loss function you're trying to minimize is the error of the input versus the output. And you're choking the information down to this latent space Z, which is kind of an information bottleneck. So you want to find the 3 best pieces of information that if you compress down to Z, you could decompress and capture as much of your image as possible. Okay. And again, we've known this for a long time. We've known this for decades as well, that you could write this problem as a linear shallow autoencoder. I would not recommend doing this for your research problem. You should try it on data to see how badly it works. You need about 10 or 100 times more data to train this neural network than if you wanted to just do a simple SVD. And the modes that you get out are not ordered by importance like in the SVD. And so there are huge advantages to linear algebra, kind of optimal linear algebra approaches if you can get away with them. But I want to point out that you can technically write this as a neural network. And what that allows you to do is relax those assumptions of it being shallow and having linear activation units. And you can instead develop a deep autoencoder network with nonlinear activation units. And what this does is if the SVD or principal components gives you a low dimensional linear space where your data evolves, a deep autoencoder gives you a low dimensional nonlinear manifold where your data evolves. So in principle, you can often find a much more compact latent space Z where your dynamics are much more effectively represented in that deep autoencoder. So again, what we're doing is we're using the neural network in a very focused way to learn a coordinate system where the data is compressed. And so if I want to abstract it, this is kind of my abstraction of that picture. We have our high dimensional data X, and we're trying to learn an encoder into this latent space Z and a decoder into the high dimensional space X. But as physicists and engineers and control theorists, what we really want to do is not just learn a coordinate transformation. We want to learn a coordinate transformation into an effective low dimensional system where we can also get a representation of how the dynamics evolve, the Z dot dynamics. So in this case, we want a nonlinear model in that low dimensional latent space. So think about the eagle, right? The eagle is in this million or billion dimensional fluid flow, but we want to understand what are the coordinates, what are the 3 variables that matter for that eagle's life and death every day. And that's what we're going to try to learn in these Z coordinates. And again, I'll point out again that knowing the right coordinate system can be integral in learning the right dynamics. Okay, so this is the Earth at the center of the solar system, and you get very complicated trajectories. Your data is hard to untangle. But when you have the right coordinate system, when you put the sun at the center of the solar system, the dynamics become much, much easier to disentangle, and you can get a much more compact representation of that f of x. And sometimes what we're going to try to do is not just learn a coordinate system where the dynamics are identifiable, but even where the dynamics are linear. So sometimes we're going to put even more pressure on this encoder network to find a coordinate system where our dynamics become linear. Okay. And if there's any questions, please feel free to jump in and interrupt. Okay, so we've talked about kind of how we're going to use autoencoders to deal with this dimensionality issue and find those patterns and the coordinate systems. Now I'm going to talk specifically about nonlinear coordinate transformations that linearize dynamics. And so I'm guessing a lot of you in the audience have heard of dynamic mode decomposition and the Koopman operator, probably. I'm going to give like a really brief overview of why we believe that these coordinate transformations exist and how we might use them. Because this is a lot to ask, right? Like 10 years ago, if you said, oh, we're going to try to find a coordinate transformation that linearizes, turbulence, I probably would have said you're crazy. That's an absurd thing to ask for. But we have some reason to think that there are these coordinate transformations even for strongly nonlinear systems where we might be able to view the dynamics as approximately linear. And so this is related to the Koopman operator. And I'm going to illustrate how this would work on a very simple example. I used to define the Koopman operator and Hilbert spaces. I'm going to just get rid of all of that and just show you an example where it works. And I am going to say at the very outset, I am showing you this example because this is the only one that simply works. Okay, almost all cases where you write down a differential equation, it will be almost impossible to find this linearizing Koopman transformation. So I want to say that at the outset, this is much harder than a lot of people say it is. But this one works. So we're going to walk through it. We have a very simple dynamical system with two states, x1 and x2. The x1 dynamics are linear. We assume mu and lambda are both stable eigenvalues. And that I'm going to assume that lambda is a bit faster than mu. So that very rapidly what happens is the x2 dynamics equilibrate so that x2 equals x1 squared. And what that means is that there's this red slow manifold where all trajectories rapidly kind of attract onto this manifold and then slowly go to the origin. Okay, really simple setup, single fixed point at the origin. And so what we're going to do is we're going to augment our state vector x1 and x2. We're going to add a third state x1 squared. And I'm going to show you that in these new three-dimensional coordinate system, we actually linearize these nonlinear dynamics. Okay, so we add this x1 squared variable, that's our y3. And now our second equation becomes linear in that third variable, right? That x1 squared is our y3 term, so that's linear. And the entire crux of the argument now relies on the y3 variable. Does the time derivative of y3, is it linearly representable in terms of y1, y2, and y3? Is it a combination of those? So let's just do the chain rule in our head. The derivative of y3 is the derivative of x1 squared. So it's 2x1 x1 dot, which is 2 mu x1 squared, which is 2 mu y3. So it is closed, it's linearly dependent on my y vector. And what that means is that I get a closed form 3x3 matrix that linearly describes the evolution of my original nonlinear system in this high dimensional coordinates. And I've shown that plot in 3D, and you can see projected onto the y1, y2 plane of this, these linear dynamics projected onto y1, y2 perfectly capture my nonlinear dynamics. Okay, so this is a cartoon to show you that yes, sometimes it's possible for nonlinear systems to find a coordinate system that makes them look linear. And if you had that coordinate system, lots of things would be easier. Prediction, estimation, and control would again become one-line MATLAB and Python solutions. You can also look at the eigenvectors, the left eigenvectors of this A matrix, this 3x3 A matrix, and you can find these eigenfunctions, phi mu and phi lambda. The way I think about these are kind of magic functions that if you looked at the world through these magic functions, everything would look linear. It would look like sines and cosines and exponentials. And we're trying to find those functions phi for complex systems like turbulence and like robotics and biolocomotion. And if you had that linearizing coordinate system, you could do optimal nonlinear control, again, using very simple off-the-shelf techniques. So, in this case, we can do an LQR in that augmented three-dimensional space. And you get now it's an LQR, there's 3 gain terms in that gain matrix. And so I have my linear terms and a proportional control proportional to x1 squared. So this is an optimal nonlinear controller. And if you look at the lower right plot, the cost versus time, essentially what you see is that if you did a naive linear model at the origin, kind of a local linear model in LQR, it's about 3 times more expensive to control using a naive local linear model than a global Koopman nonlinear model at the one that we derived. So it would be awesome to be able to do this for turbulence, right? We would be able to build jet airplanes that are more efficient, more performant, more robust. but finding these coordinate transformations is notoriously challenging. Okay, so let me show you an example that doesn't work, and most examples don't work. It's really, really hard to find these magic eigenfunctions where everything looks linear. So on its face, this differential equation actually looks easier than before. It's one ODE, x dot equals x squared. It technically is a little nastier. This one has finite time blow up, so there's discontinuities in finite time. But let's try the same trick. We're going to augment our state vector, x, with the nonlinearity on the right-hand side. We're going to add x squared. Now, again, we need this to be closed. We need the derivative of y1 and y2 to be linearly dependent on y1 and y2. So what's the derivative of y2? Let's do the chain rule. It's 2x x dot again, which is 2x times x squared, which is 2x cubed. Shit, so that's not closed. So now I need to add an x cubed term. And if I take the derivative of that, I'm going to get an x to the fourth term. I need to add an x to the fourth term. When I take the derivative of that, I get x to the fifth, and it never closes. Okay, so now you're starting to see the issue is that the Koopman operator, this was developed in the 1930s, and essentially way back then they had it was not connected to what we use it for now. This was supposed to essentially resolve the ergodic theorem, Boltzmann's ergodic hypothesis. But it was developed, and it essentially says that you can find a linear representation for nonlinear dynamics, but it is in an infinite dimensional Hilbert space of measurement functions. Of all possible measurements I could take of my system in that Hilbert space, in that infinite dimensional space, that representation evolves linearly in time. And so this is an example where, it's kind of the no free lunch. If I pick a naive coordinate system like polynomials, I don't get closed models at any finite rank. I need all infinite, dimensional representation to capture the system. And this isn't going to work for us. This is, what my friend Bernd Nowak calls conservation of difficulty. We took one hard problem, which is nonlinear control, and we turned it into another hard problem, which is infinite dimensional control. Okay. And I showed this to Clancy Rowley. He was my former PhD advisor. And, I think he was just messing with me. He scratched his head and he wrote down an eigenfunction on a napkin, just wrote it down. I am convinced now that he thought about this particular problem ahead of time, but there are still eigenfunctions that exist for this problem. So polynomials are a bad basis and you don't get closure, but there are still these kind of magical eigenfunctions that if you happened to find them, you could represent your system linearly in these phi coordinates. Okay, so how are we going to find these for modern systems of interest? If you play around with some algebra, you have your original dynamical system, you're trying to find this new coordinate phi that linearizes everything. You apply the chain rule, and you can pretty quickly derive this nasty partial differential equation that has to be satisfied for these Koopman eigenfunctions, for these magic coordinates where things look linear, these phi coordinates. And again, if you take this x dot equals x squared and you plug it into that red eigenfunction equation and you look at a Laurent series, a two-sided Taylor series, you can actually match terms and get exactly the model that Clancy just wrote down. But we're not going to be able to do that for modern systems of interest like turbulence. No one is going to be able to scratch their head and write down the turbulence eigenfunction. So we need to be able to do this with data and with more powerful representations than just a two-sided Taylor series. Okay. And so anytime anyone tells you there is a function that I need to find or represent that is really nasty, it's almost irrepresentably complex, you should have a light bulb going off in your head that that is exactly what neural networks are good at. It's one of the only things neural networks are good at the end of the day, is arbitrary function approximation. If you have enough data, they will find you a phi that satisfies that equation. Okay, and they'll represent it even if it's spiky and horrible and high dimensional. I'm going to take a very, very brief aside and just show you that you can also add control in these eigenfunction coordinates. If you happen to find an eigenfunction, one of these magic phis, and you had some affine control system, then you could essentially, again, do the chain rule and get this red boxed equation where the eigenfunction coordinates are still linear in the state, the eigenfunction state, but now you get a state-dependent actuation, this grad phi dot b times u. And so the control is a little more complicated, but you can essentially do like state-dependent Riccati equation optimal control solutions. And Ulrike Kaiser, who is a fantastic postdoc working with us, essentially used this to control lots of mechanical systems. So a couple of eigenfunctions that you can always get for free, and this is super interesting, and I don't think anyone really pointed this out before Kaiser. Conserved quantities. Anything that's conserved is a Koopman eigenfunction with eigenvalue 0. The time derivative of the Hamiltonian behaves with zero dynamics, with lambda 0 dynamics. So it's really beautiful, right? Any conserved quantity or nearly conserved quantity is approximately a Koopman eigenfunction. And so you can immediately kind of recover classical Hamiltonian nonlinear control theory in this new kind of expanded Koopman control framework. And this, we can generalize, we can relax that assumption of perfect invariance and perfect conservation, kind of the Noether's type conservations, to things that are nearly invariant and almost conserved, things that are very lightly damped. You know, we can find eigenfunctions for those and we can control those. And that happens to be pretty important because the things that are very lightly damped, at least in fluid systems or in aerospace systems, are usually the things that stick around long enough for me to care about as an engineer. Okay. She also showed some really cool ability to do lobe switching in complex systems. This is something that matters for like space mission design. If you want to hop from one orbit of a moon of Jupiter to another moon of Jupiter, you need to be able to hop these saddle points in an energy efficient way. And she can kind of learn that using this Koopman control. I actually learned about this at Caltech from Jerry Marsden when I was an undergrad. Okay, so we wrote a review paper on Koopman recently because I've been working on Koopman for about 10 years now. And there seems to be a lot of excitement in the community. There's a lot of promise of finding these coordinate systems where things are linear, but there's a lot of also confusion and kind of, I don't want to say misinformation, but there's a lot of hype. You're going to find a lot of people telling you that this is just easy. And once you get this coordinate system, everything is going to be easy. Again, that's just not true. There's a conservation of difficulty. Finding these coordinates where things are linear might be 100 times harder than your original problem. But again, in the machine learning world, you can think of this, that's an offline task. I can do that on a supercomputer, you know, at Argonne over months. But once I find that coordinate system for turbulence, I can use it online in real time as fast as you like. And so we might be willing to pay that nearly infinite cost of finding these coordinates, but it is nearly infinite. It's like extremely hard to find these coordinates. Okay, so if you're interested, you can check out this review paper we wrote. It's about 100 pages long, and it really goes into depth on Koopman control and modeling and theory and the different perspectives of kind of conserved quantities or local, you know, linearizations and things like that. Now, in practice, what most of us do is dynamic mode decomposition. This is like a linear regression algorithm that gives you a best fit model that, again, captures some aspects of the linear evolution of a complex system. Okay, so this was introduced in fluids by Peter Schmidt. Very soon after, Clancy Rowley and Igor Mezic connected it back to fluids, or sorry, to the Koopman operator. That this linear regression model starts to look a lot like this linear Koopman operator. And I'm not going to go into a lot of detail here, but basically, the dynamic mode decomposition is going to give you a best fit linear operator that marches high dimensional measurements of your system forward in time. And it's actually remarkably good at fitting your data and giving you beautiful modes like these. But it typically only works when your data is periodic or quasi-periodic. It doesn't capture transients or essential nonlinearities of your system. And the way you can think about it is the following. Any finite dimensional linear operator has a single fixed point at the origin. If your nonlinear system has transients that are given or characterized by multiple fixed points or unstable periodic orbits or strange attractors, there is no way for dynamic mode decomposition to possibly characterize those transients and that complexity. It can't do it with a finite dimensional linear model, okay? But again, finding these coordinate systems, so DMD is essentially a linear regression, an SVD-based approach. It's like basically the principal components I showed you before. You find a linear regression model in principal components coordinate system. But what you can do is you can use these deep autoencoders to find a better coordinate system in which to represent your dynamics, and then do that linear regression on that latent space to do basically DMD, add a DMD loss function in your latent space. So Nathan Kutz and I hosted a workshop in Banff in January 2017. And we had a workshop, like a mini workshop, on kind of deep learning and dynamical systems and things like that. And I think everybody in the workshop group kind of independently at the same time had this light bulb go off that DMD suffers from a coordinate transformation problem, or Koopman suffers from a coordinate transformation problem, an irrepresentably complex function phi. And that is exactly what we should be using our deep neural networks to find or to represent. And so within 6 or 12 months, there were 10 groups across the globe that independently developed a deep Koopman autoencoder. So Frank Noe's group in Berlin has a great one. Hodis Young, Sam Otto and Clancy Rowley, Takeishi from the Japanese group, and Bethany Lush from our group all kind of independently developed these Koopman encoder networks where we have linear loss functions in the middle. Sorry, I skipped a slide. Where we have linear loss functions in the middle that constrain the dynamics to evolve linearly. Ours is kind of custom. We have a parameterized K matrix so that we can deal with systems that have a continuous eigenvalue spectrum, but that's really just a technicality. And what we found actually is that the community is very split in whether or not you use a dimensionality reduction, kind of an autoencoder network like the top, or whether you actually do the more machine learning-y thing and blow up to an even higher dimensional space like a kernel method would do. So go from, you know, your 10-dimensional or 100-dimensional system to a bajillion dimensions, work in that system, and then come back down. And there's pros and cons to both approaches. I personally like the autoencoder on the top because it highlights the few key eigenfunctions in phi. It's more interpretable, and it's, you know, generally more trainable with less data. But the bottom network is kind of interesting. We think actually that a lot of these continuous spectrum systems, so any of you who have done dynamical systems and remember the Poincare-Lindstedt theorem, sorry, this is super obscure, are going to remember that if you have some linear dynamics like a linear pendulum, but you start to add in the epsilon cubic nonlinearity as you start increasing your amplitude, you know, your eigenvalues are going to start to shift. And you do that by adding in harmonics, 3rd, 5th, 7th, you know, 9th, 11th harmonics of that fundamental frequency. So Nathan Kutz and I believe that that's what this big K matrix is doing. It's basically blowing out a bunch of harmonics of your few Koopman eigenfunctions that actually matter. And that's how it's approximating these continuous spectrum problems. Now, of course, I think that we would prefer this smaller network K that just finds those, you know, nonlinear oscillators directly. Okay, good. I have a little time left, so I'm going to give you kind of the next piece of the talk, and then I'll break for questions. So I've talked about nonlinear dynamics, high dimensionality, but I really want to talk about how do you discover nonlinear models from scratch when you have no models. And this also fixes a lot of the DMD Koopman problems that we have of like asking for linear dynamics is a little too aggressive for a lot of the problems we care about. So I'm going to take this opportunity to kind of give you my soapbox feeling on machine learning for a couple of minutes. That, you know, and I'm guilty of this. We all use neural networks. They're super powerful. They're great for arbitrary function approximation, but they tend to be quite opaque or black box. They're very hard to interpret what your neural network is doing. And they also suffer from overfitting and, you know, vast data requirements. They're not that great for engineering purposes in a lot of cases. They're great for Google and Facebook and Amazon, who have infinite data and infinite computational resources. We as engineers need interpretable and generalizable machine learning models. So I could define what these are, but we would get in a fight. Instead, what I'm going to do is I'm going to give you my example of the quintessential interpretable generalizable model. So I think F equals MA is a lot more interpretable than a 1,000,000 parameter deep neural network. So F equals MA has 3 terms, F, M, and A. They have units. We can write them down for a particular problem, and we can explain and communicate and analyze them. That's what I mean by interpretable. It's generalizable in the sense that Newton can learn F equals MA from apples falling on Earth. That's how the story goes. And it's still valid when we land humans on the moon or on Mars. That's like the ultimate in generalizability. Okay, so I guarantee that if we had videos of apples falling, maybe 5,000 videos, we could build a deep neural network that would reproduce new videos of falling apples. But that neural network is not going to be useful to land humans on the moon. Like, I can almost guarantee that. So this idea, this F equals MA, what makes it special? What makes it interpretable and generalizable? Well, it's only got a few terms, and it's as simple as possible to describe the observed physics, but no simpler. So this principle of parsimony has been the golden rule of physics from Aristotle until Isaac Newton and past, up to Einstein. The idea of parsimony, or the simplest model that describes the data as being the right physics. And so when we say generalizable machine learning, what I would say that the only models that have ever generalized are physics models. That's almost a working definition of physics models. There is a physics of your brain, and it's the rules that generalize from person to person or situation to situation. And so how do we as mathematicians and scientists develop models now with these enhanced machine learning optimizations that remain interpretable and generalizable? I would argue that our two tools at our disposal that we can use in optimization problems are low dimensionality, again, F, M, and A, there's 3 variables, and sparsity, as few interactions as possible between those variables that are necessary to describe the physics. Okay, so fast forward from Isaac Newton, in the modern computational era, that looks a lot like this Lorentz 1963 model. So Lorentz 1963 is a simple, low-dimensional ODE model that describes chaotic Rayleigh-Benard convection. So it describes a very high-dimensional nonlinear process. But if you look at the Lorentz 1963 model, it checks our 2 boxes. It is low-dimensional. It's expressed in terms of x, y, and z, which are the amplitudes of 3 spatial modes. And it's sparse. On the right-hand side, out of all the possible interactions between those variables that could give rise to these dynamics, this one is quite simple. There's 7 terms, and most of them are linear. Okay? So that's what we want. We want to learn models like that from data. That will be more interpretable and more generalizable. And so for the last couple of minutes, I'm going to show you a method we have in my lab developed called SINDy, the sparse identification of nonlinear dynamics, which is essentially a data-driven Lorentz 1963. It automates what Lorentz did with his, big brain and great computational resources and fantastic grad students. So we're going to look at data from this Lorentz 1963 system. So we know that there's equations, but we're only going to have access to the measurement data. We measure x, y, and z in time series, and we're going to compute the derivatives x dot, y dot, z dot. Now, what would DMD Koopman do? So the simplest thing you could do is build a linear regression model, a best fit least squares A matrix that's 3 by 3, that is the best fit of x dot as a linear combination of x, right? That's what DMD dynamic mode decomposition would do. And this is almost like a cartoon or a caricature of why DMD doesn't work in so many cases for transient systems, for truly essentially nonlinear systems. Because that little A matrix has one fixed point at the origin. There's no way it could possibly capture the rich dynamics of the Lorentz system, which has multiple fixed points and unstable periodic orbits and a chaotic attractor. There's no possible way a 3 by 3 A matrix could capture those dynamics. So instead, what we do is we augment our right-hand side with more candidate nonlinearities that could describe the dynamics on the left, that could describe that observational data. In this case, I'm building polynomials, x squared, xy, y squared. Again, these are functions we can build out of the data we have. And now the task is to try to uncover the fewest, the sparsest linear combination of these dynamics terms that describe x dot, y dot, and z dot. And again, 20 years ago, this would be a combinatorial brute force optimization that would not scale with Moore's law. But now with advanced optimization techniques, data-driven, I would call them machine learning techniques, sparse regression is a commodity algorithm. There's dozens of algorithms on the market that will give you the sparsest combination of theta that equals x dot, y dot, and z dot. And if you look at the terms that are highlighted, they tend to be exactly the terms that generated the data, the real, true dynamical system. And of course, that means it will generalize better than a big neural network that's just fitting the vector field. Okay. I'll also point out this theta matrix. You can build it to include things like the parameters sigma, rho, and beta. If you can measure the system at multiple parameter values, you can build those in and get bifurcation models. If you have a control vector, some U input that you're using to force your system, that can be a column, and you can add nonlinear columns of the state and the control and learn how the actuated system behaves and use that for model predictive control. So if you're interested in trying this out yourself, we have a software package, SINDy, that essentially, codes all this up, and you can try it on your systems. We also have SINDy MPC that directly interfaces that with the MPC optimization, so you can use that for real-time control of nonlinear systems. And maybe one of the last slides I'll show, if we could just rediscover Lorentz 1963, that's not that impressive. But in the intervening kind of 5 years, we've used this to describe lots and lots of nonlinear fluid flow problems and plasma physics problems. So for every single problem I'm showing here, a sphere-Mac fusion reactor, a turbulent wake experiment, an electroconvective system, in all of these examples, we've been able to identify low-dimensional, sparse, nonlinear models that capture the essential physics and can be used for real-time optimization and control. Okay, so I don't have time to tell you all of the other things we've done. Maybe if there's questions, I can tell you how we've developed these models for systems with hidden variables and latent dynamics, how we've incorporated model predictive control, what happens when we're not measuring the right X variable or the right latent space, how we've incorporated this with neural networks. I guess, but for now, I think I'll end and see if there's any questions from the audience. Thank you all very much. And yeah, if anyone has questions, please just jump in, or maybe if one of the hosts can read them from the chat.
Yes. Thank you so much, Steve, for the wonderful talk. So there were a few questions on the chat box. One about this transformation and what happens to the fixed points. The question was, how do you ensure that the properties of the fixed points are preserved by the transformation? I believe they're referring to the coordinate transformation. Is there a way to construct the transformation to be canonical?
Yeah, this is a great question. And this is actually, it's one of the questions that it took a long time for us in the community to even pose that question correctly. So that's a really good question. And again, this is a perspective we take in this Koopman review paper. And this is actually figure 1 of our paper, because that's exactly the right question. So here I'm going to try to give you a very brief overview. So those of us in dynamical systems and control remember the Hartman-Grobman theorem that, if you have some kind of fixed point in a more complicated nonlinear system, if it's a hyperbolic fixed point, then you can locally linearize, and kind of the local dynamics are topologically conjugate to the true nonlinear dynamics. So you can do local linear control theory and stuff like that. Now, one perspective of Koopman, so in the upper left panel, this A panel, those are my local linearizations using kind of like naive classical linearization. One perspective of Koopman is that I can build a coordinate transformation that will expand one of those. If I pick one fixed point, I can zoom in on that fixed point, and I can expand that local linearization to be a more global linearization up until I hit another fixed point. So I can take that little pink region and I can make it larger until it hits another fixed point or kind of invariant set, like that homoclinic orbit. So that's as good as we can do preserving the nature of that fixed point. But the other perspective in panel C is that there are truly global Koopman eigenfunctions, like these conserved quantities, the Hamiltonian energy, for example. And now we're looking at the energy level as a Koopman eigenfunction. But if you notice, at a given level, there's a lot of ambiguity. Like, for example, if I'm at the bottom of either of those two wells and all I'm measuring is the Koopman energy, I don't know if I'm in the left well or the right well. So this is deeply related to Noether's theorem and to conserved quantities, that if I'm using one of these conserved quantities as a Koopman eigenfunction, if I'm using a global Koopman eigenfunction, I'm kind of using that symmetry to fold up my state space, and all of those fixed points kind of get identified to one fixed point. So essentially what would happen is, those two well fixed points become one fixed point in this global energy. And so again, this goes back to the no free lunch idea. Like, there are global Koopman eigenfunctions, but they will strip out local information about individual fixed points. Or I can build a tailored Koopman kind of zoom in to a specific fixed point, but it will say nothing about my other fixed points. And so you kind of can't have both. What you can do is, for example, in panel B, I could build 3 Koopman models for domain 1, domain 2, and domain 3. And I could also have a handful of global Koopman eigenfunctions that like energy and other conserved quantities. And I could use some kind of smart interpolation and or switching, to kind of switch between them depending on a higher level control objective. And that could be pretty interesting. But you're not going to get like one global Koopman that makes everything simple. And that took us years to figure out. I mean, that took us 5 years to really convince ourselves in our guts that, there is not just one simple model that's going to make everything linearly controllable.
Awesome.
Great question. Thank you.
Yeah, so there are a few more questions. I'm going to ask the person who has asked the question to unmute themselves. Is Jordan?
Yeah, hello, and thanks a lot for the talk. It was really amazing and great work. And I just had this question because you were discussing, generalizability and interpretability, which of course it is always really important, but I'm trying to look through the glass of a practical engineering applications and certification of let's say you're using a control system or estimator based on such type of reduced model. And what you really want to know if you want to use it on an aircraft is, can I legally certify it? And to legally certify it, I'm not sure if there is a requirement to be interpretable. What would be mostly required would be that you kind of know in the range that you're going to use this estimator, that you can predict uncertainty traceable to some fixed standard, that you can prove the credibility of this system. So I'm just asking the question, how really important is a model to be interpretable? Isn't it more important to be traceable and to be proven that in certain region of operation you can have you can trust the uncertainty estimation of this reduced model?
Yeah, I think that's a really good question. And I mean, a lot of it boils down to what you want to use your model for. I think humans are going to be increasingly using these machine learning optimizations as techniques and tools to solve the problems that they want to solve, whether it's optimization, sensor placement, control, modeling, you name it. I just heard a quote by some computer scientist that basically said that, in 20 years, all of us are going to be out of business and every line of science is going to be a field of computer science. And I think that's pretty, that's optimistic, but I also think it's missing the point that all of these things are tools to be used by expert humans in the engineering problems that they want to solve. And if you were thinking of these as tools, I would like to understand how they work, and I would like them to have the essential characteristics that give me faith that they will generalize. So interpretability is something I personally want because I like to do physics and I like to understand how things work and when they'll break and bifurcations. Generalizability is more important for control. Because when you turn your controller on, if you're doing a good job, you're trying to steer your system potentially away from where you got all your training data, if you're doing something more complicated than just stabilizing a fixed point. And so generalizability is super important for that. And again, I think sparsity is essential for generalizability. But I guess maybe to answer your question more concretely, when you do these SINDy optimizations with control, so now we have a control input and we're essentially doing nonlinear system identification, input-output modeling, you can get estimates of kind of how accurate these models are, what the condition number of this theta matrix is, kind of how much uncertainty there is on what dynamic terms are being activated. Nathan Kutz and others, Robert Niven, I think there's a few papers that have essentially built a kind of Bayesian SINDy approach where you absolutely can put uncertainty bounds and manage the uncertainty in these models. And we're currently developing active techniques so that if you have systems that are actually adapting in time, you can rapidly, kind of abruptly recharacterize the system and actively gather points and apply control inputs in an active learning strategy to minimize your uncertainty, to kind of maximally improve the predictive fidelity of your surrogate model. So again, someone who spends more time thinking about like real aerospace certifiability would need to, fit that into that framework, but it's absolutely possible with this. But it's a great question. That's like, that needs to be done.
Thanks a lot.
Yep. Thanks. Other questions? Yeah.
Jack, please go ahead.
Oh, yeah, thanks so much for the talk. I was just wondering, with this SINDy approach, how does it change when you only have access to outputs? the model instead of observations of the state?
Yeah, so that's just a super interesting question. And there are two incredibly interesting lines of work that have that grad students and postdocs with Nathan and me have worked on that I can show you. They're a little involved. So maybe the first one I'll show you is this one, because this came later actually, but this one's a little easier to understand, which is, let's say I have this labeled as X on the left here, but it doesn't have to be the full state. This could be the output, a high dimensional output measurement of your system. Let's say I have a camera, observing a system, and I have the pixels of the camera as my high dimensional state. What Kathleen Champion did was essentially merge this autoencoder idea with the SINDy idea. So it's kind of like that Koopman autoencoder, but instead of requiring the dynamics to be linear in the latent space Z, Kathleen is adding these custom loss functions to make it sparse nonlinear in that latent space Z. And so if I have a high dimensional measurement, output measurement, I can often infer a reasonable latent variable Z that gives me these sparse dynamics. So kind of learning that right coordinate system. Now, if my measurement is kind of lower dimensional or only captures partial information about my state, then what we would do is augment that with time delays. So we would kind of augment with time delays and use the Tockin's embedding theorem, and then do something similar here. We'd either do an autoencoder with SINDy, or it turns out, and this is just fascinating, I'll show you, one little picture here. We were playing around with SINDy for chaotic systems, and a reviewer for the original SINDy paper back in 2015 asked us, what if we only had the access to the first state variable x1? So that's, I think, the question you're asking is, what if I just measured the output x1 and not, y and z? So we essentially built this time delay model. And when we applied SINDy to the time delay model, what we found is that the best, most parsimonious model that described the data was a linear model, a sparse linear model. And so that gave us this reconnection back to Koopman theory. So again, there's a linear model that evolves these time delay vectors. And that linear model is related. It gives you essentially a representation of the Koopman operator in time delays. So what this showed us is that probably the best coordinate system to actually measure systems to get a Koopman linear representation are time delays. And this is, again, deeply related to classic system identification from the 1980s and even all the way back to Ho and Kalman in 1960, but really the eigensystem realization algorithm, what Wong and Papa in 1985, that was a linear version of this Havoc, this Hankel-Koopman approach. And so, I did a lot of ERA, eigensystem realization work in my thesis for nonlinear systems. And we were always surprised how well it performed even on nonlinear fluid problems. And it's because of this connection to the Koopman operator. So long story short, if you have latent variables, try time delaying or some kind of a Koopman a SINDy autoencoder framework. Yeah, thanks for the good question.
Thank you.
Okay.
So, a lot of these things reminded me of non-equilibrium thermodynamics, where you're sort of looking for these linear functions of a highly chaotic system that are like relaxing in a linear way. So I was just wondering if you've thought about sort of basic fundamental physics implications of Koopman theory on sort of a theory of non-equilibrium thermodynamics.
So it's such a cool question, and it's actually it's very appropriate given the history. So if you go all the way back to 1930, right? No one was talking about, coordinate transformations that linearize nonlinear dynamical systems to make control easier. That was not the idea of Koopman way back when. The idea of Koopman way back when, I'm trying to find a slide that looks like Koopman. The idea of Koopman way back then was essentially to rectify operator theory and nonlinear dynamical systems, right? Because quantum mechanics was being represented in this operator theoretic standpoint, and all of classical dynamical systems was in this kind of Poincare geometric dynamical systems. And Koopman was just trying to unify these. And it ended up being useful because it allowed Birkhoff and von Neumann to prove the ergodic hypothesis of Boltzmann. And it basically took kind of the last missing piece of the gas dynamics, dynamics puzzle, and Koopman was used to kind of tie that up with a bow. And so I think that there's a ton of promise to potentially use those same ideas for things like Navier-Stokes, kind of coarse-grained Navier-Stokes from atomistic models, right? Which is an open problem in physics today, is going from kind of atomistic models of liquids and actually deriving things like the Navier-Stokes equations. And so again, part of the reason is because turbulence does not admit a simple statistical closure like gas dynamics does. And it's, every approach to doing this, my colleague Bernd Nowak has spent decades, doing great work on this, but, there is a fundamental missing piece there. And so the hope of a lot of us is that, the same way that Koopman filled in that missing piece in the gas dynamics picture, we might be able to do the same thing for like a turbulence closure picture. But that's a very ambitious goal. I know people are working on that, but that's like Nobel Prize stuff.
Great. Any other questions?
Yes. Thank you, Stephen, for the talk. The linearization you're using is called Koopman linearization. Yes, I can give you a reason. I'm not very into this linearization. I give you a reason. When we back to the first example you given, did you notice that do you remember that example?
Yes. Yeah.
The linearized model is not equivalent to the original model. Do you notice that? Because the y1 and the y3 is fixed in the manifold of y1 equals y3 square. So even you do this linearization, it's still not equivalent. That you have to add a constraint.
Yes, that's an extremely good point. So actually, you'll notice this three-dimensional picture has this red, green, and blue manifolds. That's exactly right. You have to satisfy those additional constraints that y3 must be y1 squared. Otherwise, you'll get spurious dynamics. There are other dynamics that are non-physical in this three-dimensional system, and you have to restrict it to this manifold. So you're right. I am not trying to convince anyone that you should use Koopman for modeling or control. I think it's an interesting perspective that is very, there's a lot of thought and effort that goes into this. What I'm more interested in, for example, there are connections to classical methods like Carleman linearization and more modern methods like feedback linearization. I think there are connections that can be made, but you're right. Like, sorry, I interrupted you, but you're right there. Like, you absolutely have to constrain this three-dimensional system to live on one of those submanifolds. Otherwise, it does not capture that system. You're right.
Yes, I'm just actually I believe if you ignore this part, you can do something engineering. On engineering, you can do some beautiful result out, but the consequence if you remember you ignore this constraint. For example, the next slides you do some optimal control based on the linearization model. The control law is not the actual optimal control law, right? If you ignore that constraint.
Well, so this is important. We're not applying this to the three-dimensional Y system. We're just using that as a surrogate model to design the controller. We apply everything back to the original dynamics in X1, X2. So the middle Y variable is just a proxy. We're still working on the first equation in just two states, and we're only using this U, which is a function of those two states.
Oh.
So the constraints are satisfied because we're working in the physical system.
Wait.
And this is a subtle point. Like I'm not 100% sure that you're not right, that there could be things that could go wrong here. But at least in this example, we're working on the physical state where the constraints are definitely being satisfied, and the output is just a nonlinear function of those two states.
I would also like to add to this that if we use a Lagrange multiplier and incorporate the constraint for the third case, with the three variables, you could actually have the cost function to include the Lagrange multiplier and the constraint.
Yeah, that's a good point. You definitely could in this control optimization. Yep. Great questions. Any other questions? Yeah. I realize it's getting late. I can stay around, but I realize other people might have places to be.
Yeah, there was a lot of interest from the audience, many interesting questions. If there's a quick question, maybe we can take that as the last one.
Hi. So my question was that is it possible to obtain Koopman operator for the systems having a limit cycle?
Is it possible to obtain Koopman for systems in a limit cycle? Yes. So the original fluid systems, like the dynamic mode decomposition of Schmidt and of Rowley, most of the fluid systems that were originally analyzed were in some kind of a stable limit cycle. Or maybe they were a little turbulent, but they exhibited some dominant frequencies that kind of, some dominant recurrent frequencies. And besides fixed points, those are kind of the only other types of things you can reasonably expect to characterize with Koopman. So you'll do a great job of characterizing of essentially compressing the data and getting modes out when your system is on a limit cycle. But unfortunately, it doesn't tell you anything about if you kick the system or if you have a transient or you perturb that limit cycle. Like once you excite the real nonlinear dynamics and you're out of that balance in that limit cycle, those truly essentially nonlinear dynamics are not going to be captured by Koopman. But if you are actually on a limit cycle, you can characterize it very nicely. And that's actually what the first DMD papers did, exactly that. So Clancy's in particular talks about literally linearizing these systems on a limit cycle. Great question.
Okay.
Yeah, thank you.
Thank you.
Okay, great. So in the interest of time, let's stop here and let's thank Stephen again.